contribute to the challenge of the global warming in three areas. Firstly, how they help to understand what is going on, the observation and the monitoring. Secondly, how the high-tech can actually improve some of the services usages that are deployed or that they will be deployed in the future as well. And thirdly, how we can put this technology even to become more sustainable, more, let's say, eco-friendly than they are in our common lives. So if this plan is okay for you, I'll start with the first element, which is the monitoring, and I will take the activities we are doing for space in this arena. As you of course are all aware, is that the global warming is a global problem. It's not limited to a given country. It is going all around the globe. And in order to understand what is going on, in order to monitor the human activities and their consequences, it is important to have a global understanding. And space is the perfect place to do it because you can see everything with a good revisiting rate for the different points. The one element I would really like to highlight is one of the satellites we are currently developing for the European Space Agency within the Copernicus program, which is a real breakthrough in a way, because it will monitor the carbon dioxide in the atmosphere with the resolution that has never been met, 2 by 2 kilometers, which is, standardly it was possible something like 100 kilometers so far. And it will have the capability to distinguish the part of the human activity. So these two elements together, the resolution and capable to really identify and measure, quantify, and position in time what the human impact is very clear, of course, to take then the right decisions. And this will be done globally at the world scale. And each of the point of the Earth will be observed. At least monthly or a few times per month. So that's an important element we are bringing to the monitoring scheme. It is quite unique and in advance. The second one is an altimeter, which will actually measure again in a disruptive way what is going in the polar regions, because it will distinguish the depths, the thickness of the ice which is on the ocean. From making the distinction from the accumulated snow, which is in the polar region, because we have better accuracy, we have actually different modus operandi of testing that, and by the way, we will also increase the accuracy. And again, I guess it's now very well known that first the polar regions are suffering a lot in many circumstances in the first place of the global warming, so it's important to monitor them, but they also contribute to what is going on in a positive or in a negative way, both. So this program is ongoing. It's actually completing a kind of portfolio that we have in a space observation that is combined with the supervision monitoring of the oceans, the sea. You know what the pollution is, like the catastrophic flood we had in the south of France and Italy. I mean, many rivers actually have accumulated water level, which was tremendous. They are bringing, earth and dust and debris to the sea. We can see these from the sea and actually evaluate how different rivers are going wrong in a way. But you can do other things by doing that. We are also measuring with this is called Poseidon as a satellite. We are measuring the altimeter of the altitude of the sea. It's not flat actually. It depends on several factors, including thermal and the winds. And this again is very important to measure the model of what is going on in the oceans, because they do dominate what is then happening on Earth. And historically, we are the leading supplier of the satellites for weather forecasting, the Meteosat family, which we are already in the third generation. So all in all, this observation capability is quite unique in terms of performance we are achieving and we are planning to develop. And we believe, like every problem, it's hard to solve it if you don't measure it. So that's the first element. The second one, which is the contribution of the technologies to diminish the impact of some of the things we do, and I will talk about the transport, which obviously is an issue in this environmental debate. What I would like to highlight is that some of the solutions are long-term, which we are currently discussing, at national levels and European levels and so forth. So there is a long-term roadmap. But some of the solutions I will mention are here today. So it's not that kind of planetary plans that will happen to be true in 10, 20 years from now. It's a roadmap, and the roadmap begins now, start now. So let me start with the terrestrial transport first. So the trains, I think they are quite often and rightly so highlighted as being already quite environment-friendly modus of transportation, and indeed the calculation per kilometer per person transported is very favorable for the train because it's mass transport and so forth. Yet it's always useful to decrease the impact of the carbon for this modality too. If you look to what are the origins of the energy consumption and hence the carbon dioxide impact for the trains, you will see that the part that is linked to the mobility, so really the debate of these tiny supervision parts, tiny in terms of energy consumption, might be very important. We have today two solutions that are installed in the field. One is based on big data and actually collecting a lot of data around the tracks and the train and providing advices to the conductor, advices which actually are bound to a contract to diminish the power consumption of the line, and we are measuring that over a year, and then we see if the promise is at the rendezvous. The second solution is called Green CBTC. CBTC stands for a standard. It was invented by Thales, but it's a standard now about the trains that communicate between them and between the stations or the control system for the signaling. But we use this supervisory layer on the train to provide an extra function, which is green, which actually is the optimization of all the trains in order to reduce the energy consumption. One example, in a very dense area of subways or metros, if you do nothing, you might have the possibility to have several trains departing at the same time. When they depart, they ask for a lot of power to put the engine in movement. So you have a kind of, in terms of energy consumption, you have a kind of peak over time. And usually the power supply layer of the urban transport is like internet. It has to be designed for the maximum power demand. But in practice, this maximum is only short time. The rest of the time, it's much lower. So what our system allows is actually to smooth this demand. And just by changing, a few seconds, the departure from of each of the train to actually average this demand over time, and hence to be able to use a more reasonable power supplies in the whole system. And of course, there's a net benefit. Both systems together can be complementary. And in terms of what is the possible reduction in terms of energy, we are talking about 10 to 20% of the totality of the energy, which is very, very, very important. And bear in mind that in a way these are systems that are add-on the existing systems, which actually improve the situation before we go to a more futuristic train or whatsoever. So it's very valuable. It doesn't make a fully green train, but it makes a much greener train. In a way, the same approach, even though technically it's slightly more sophisticated, but the same approach, we do follow that for the air transport. And I'd like to address two areas. One is more, I would say, plane-centric. The second one is more global in terms of air traffic. For the one of train-centric, you might know that Thales is, well, actually is providing what we used to call the brain of the plane, which is called the flight management system. Now we are developing a solution that will be very soon on the market, which is called the Pure Flight, which is a new generation of flight management system, fully connected, agile, capable of combining safety data and open data, and enhance the dialogue with the pilot, and capable to provide a better solution for the plane trajectory that will actually consume less energy. As you may certainly know, that the energy depends on, of course, the route you are following. It depends also on the time sequence for reaching the right altitude and for the time sequence and the trajectory when you land. This is what we call in our jargon the 4D trajectory, the 3D of space and 1 in time. So optimizing that, you can you can reduce the power consumption. The second aspect is linked to the air traffic monitoring, and we are currently developing a solution which is called air traffic flow management, which is again a quite data intensive solution, which will bring together all the data, which will be in the first phase used for the scheduling of the planes. As you might know that all the planes, the time of departure is, of course, it's programmed to a certain hour. That's what on your ticket, but in fact it's anticipated and possibly controlled during the days, hours before the flight really occurs, and might be changed depending on any changes that occurs. Could be that the weather is very bad in certain region, could be that one plane is not available, and as you know, because the things are so much interconnected, a local problem becomes can actually propagate in the overall traffic, and henceforth disorganize, or at least having something that is less optimum. So the work we are doing is actually to improve this part of the scheduling, including with including the energy consumption as one parameter of the optimization. To make it briefly, to put it briefly, the combination of the two techniques, the one that was plane-centric, the one that is traffic, combined together, we are again in the average of in the 10+% improvement of the energy. And this is interesting because, as you know, there are plans about having green planes in the future, and this big program starting here and there on that. Well, this will take some time. It's interesting to have a solution in parallel that can improve the situation as we have it today, knowing that this solution will also bring benefit to the other next generation planes. So it's a sustainable and long-time solution, but which will be available very soon. So this is the one example on how technology can contribute to decrease the environmental impact of the things that people use and will use in the future, which is mobility. Even though in the present pandemic crisis we move a little bit less, but hopefully we will start to remove again because we need that. The third part, which I would like to summarize with you, is how we can make these digital technologies also more environment friendly. I think there has been quite a few discussions already in different communities with the fact that, well, the digital itself is actually consuming energy and therefore is not neutral in terms of impact. To be true, the impact of digital technology is twofold. One is the one that was just explaining is improving the systems by 10% for the transport or 20% that was just mentioning. There are other kind of optimization that you can do with digital in production and so forth. And we can claim, actually, and that's certainly true, that the positive effect of the digital are higher than the negative one, which is consumption of electricity when they are in run. It's probably is going this way. However, we as Thales, we don't stay there. We would like, whatever takes and whatever matters, improve the situation of the digital system and decrease their power consumption. Now, how do we do that? And I will a little bit center my discussion about the artificial intelligence, even though by doing so I will talk about data and communication and a few other elements. If you know some of the data that are available for more the consumer market, like the carbon footprint of our mobile telephony and other devices, you know that there's actually two kinds of big contribution. There is one which is linked to the production, the development, the factory consumption, the raw materials that you need to extract, and so forth. And then you have the part which is linked to the use. And for the consumer product, without being specific on the numbers because it depends on the case to case, but roughly speaking, the two parts are equivalent. There is as much carbon dioxide production during the fabrication as it is during use. And from this perspective, one can understand that in the consumer market, the rapid obsolescence of terminals is a problem, because every time you change your device, you have, before you start using it, already the 50% of the impact on the environment through production. Well, that's a real problem. Now, in the professional world, obsolescence is not coming so quickly. What we are, developing has usually a longer period of use than what we use in private life. But still, so we are more in the 20-80 ratio, if you want a number, just to fix the idea. I would say 20% in the production, 80 in the use. But despite that ratio, we still are interested to decrease the part which is done in production. So it goes in two directions. The first one is that we actually are using more and more what is called eco-design, which is actually designing a product or a system with a full life cycle view and deciding in different steps which solution is better for the end of life carbon footprint. So this is eco-design. The second one is what we call, or not only we, I mean the community, software-defined something. Historically in defense, we started a long time ago already with the software-defined radio, which actually allowed to have different radios for the soldiers, for the air forces, for the forces in general, different kinds of radio that can be adapted to different situations. So they actually evolve through software, and they have per design a flexible hardware that allows this evolution. So hardware fabrication is done once, and actually the different version goes through software updates. This is software-defined radio. Now we are doing all our radars in the group are software-defined radars. The sonars are software-defined sonars. We have telco satellites, which are software-defined telecommunication, which is really for the first time because it's very difficult to do. So far, people have been forced to put in orbit another telco when the one that had been used was not, anymore compliant with the needs. The next generation, the current generation we are developing, actually doesn't need any more this kind of approach. It's much more flexible, it's programmable, and we can do that in the telco networks as well. So these two ingredients, the second one is actually pushing the obsolescence further away in time. The first one is a kind of holistic view on the lifetime carbon impact through the initial design. Now let's go to the use phase, the 80%. And talking about artificial intelligence, there are a few elements that are pertinent for the environment debate. The first one is when you design a neural network, which is one modality to implement artificial intelligence. we are used to put power consumption as a request. Why so? Because very, very often we put this AI on an embedded system, in equipment which is embedded. When you use AI only in the cloud, then you don't matter that much if your AI is optimized for the energy, because in a way it's a shared facility. It's in the cloud, which has anyway immense capability in terms of processing, and so the effort is more on other parameters than consumption. In our case, we put this as a very strong constraint, and there were examples of what we developed. We have been developing hardware equipment, the processors, neuron processors that actually did consume 10 times less power than commercial electronics, because our system needs that low consumption. So that's one idea. The second is that we don't use only deep learning algo, to be short, to make AI, because we have other elements that can actually open the avenues to less demanding AI, yet as performant, in some cases even more performant than deep learning. It's called semantic or symbolic AI, hybrid AI. That's something that is in a way quite unique for what I would tell the critical systems that actually need to combine the trust, certificability of the algo, which is not something that is requested in consumer market. And hence we have different approaches. And it happens, which in a way is a very good news, is that we can actually increase the trust in this technology by simultaneously decrease the carbon dioxide footprint. And I think that in the current debates, where many people believe that there is a price to pay to be greener by reducing the performance, well, this is not always true. You can have sometimes the best of the two worlds, and that's certainly what we are doing in AI. The second element of these technologies is data. And data, well, actually they consume because they are stored, because they are communicated, and so forth. So, and when you put this together with the kind of common feeling that the more data you have, the better you are, you might have a problem. Well, the problem is that the quantity of the data by itself is not a quality by itself. It's just a quantity. If many of your data are not relevant or you don't use them, well, they are just data. So we have to distinguish what data are useful from what the data are as such. So we are more in a trend of shifting to smart data and different ways of reducing the quantity of the data that are needed for certain results through the fact that we have a lot of knowledge, we have simulated data, we have another approach which allows to make the whole system more frugal. The second part of reducing the impact of the data part, because of course there are some, is actually also to design the system where the intelligence is distributed at the edge of the network or embedded on the platform, and where not every time there is a need to communicate and exchange all the data from an edge of a network to a central cloud. Because this, of course, it's used in consumer, this is widely used, but from an energy point of view is not very relevant, and from a performance is not always needed. Depends on what you know. So in a way, we are designing a little bit more sophisticated networks that again combine the performance, the trustability, which sometimes is better not to communicate, also stay local, and the energy consideration. And lastly, the part of the electronic which actually embed all of these functions. Well, I said already, we have been forced to design our own circuits with minimum consumption. So we are very kind of focused on having electronics that consume as little as possible, because in many of our systems, the thermal management just naturally is the burden that we need to reduce, and so there's even no chance actually to consume more. So we try to consume less. So that's something that we do already today as part of the design and the solution. But we have on this part also a longer track which is working on a new generation of electronics, and we do that with academia. This electronic is called a spintronic. This is a completely different electronic from the one that we are used to in our computers, which use transistors and CMOS and this kind of stuff. The spintronics use actually nanotubes, nano devices, which are very, very tiny. It actually communicate by magnetic field. They don't have wires. They communicate by magnetic field. We can, and we did produce neural computers with this technology of moderate size so far, but we run algorithmics for the voice recognition and numbered recognition, things like that, and by benchmarking with other techniques, we were very good. But the nice thing about the technology is that structurally it consumes much less than the electronics today where the neural networks are implemented. The reason being that when you use, I would say, the PC type electronics, the CMOS, the neuron and the synapses are approximated by digital function of, so you need several tens of transistors to mimic a neuron and the synapse. And that's heavy in terms of energy. In spintronic, you need one device for both the neuron and the synapse. So it's much easier. Of course, there's some kind of sophisticated physics behind, but that's no problem. That's invisible for the user. So we're investing in that. It looks promising. It has many echoes in some of the international high-level publications, like Nature. We had several papers in Nature about these breakthrough, and our colleagues from other institutions are looking to this carefully. So this again shows you what I wanted to in a way highlight, and I will conclude with that this expose by saying that we actually position our activities over a long span from today to tomorrow, and sometimes tomorrow is really tomorrow, but from today to tomorrow, the energy, the high tech and the digital is not necessarily the enemy of the planet. I mean, we can use it smartly by taking care at the different phases, and we really believe this is a strong commitment of the group, actually, because we are formally engaged on this route. Thank you so much.